Consider a block sliding down an inclined surface in which the friction between the block and surface is very small, but cannot be ignored. How would we represent this statement with a work energy bar chart? We need to represent the initial energy on the bar chart. Since the block is not moving initially, it has no kinetic energy. But the block is above the ground level, so it must have some initial gravitational potential energy, say about 4 units. Notice there must be an interaction with an outside force, friction. How will we deal with that? It will be work from an outside source, and it is work done against the system. Now we need to decide how to deal with the frictional or outside force interaction. When the block slides down the incline will hinder its motion due to the frictional force that it will exert on the block in the direction opposite to the motion of the block. This force will be applied during the distance that the block is actually moving. To give this interaction a value, let's assume that it gives 1 unit of work to the block. Since the work due to the frictional force is in the negative x direction, the work will be a -1 unit. Now we will repeat the process for a car which skids from a high speed to a stop across level ground with its brakes applied. The initial state is the car traveling at a high speed, and the final state is the car at rest. Initially, the car has kinetic energy, since it is moving, but does not have gravitational potential energy, since the height is 0, or elastic potential energy, since there are not any springs present. In the final state of the car, there is neither kinetic energy, since the car is at rest, nor potential energy, since there is no height nor springs. The force of friction between the tires of the skidding car and the road does work on the car. Friction is an external force. Friction does negative work since its direction is opposite the direction of the car's motion. Consider a skier that starts from rest on top of hill A and skis into the valley and back up onto hill B. The skier utilizes his poles to propel himself across the snow, thus doing work to change his total mechanical energy. The initial state is on top of hill A and the final state is on top of hill B. Suppose that friction and air resistance have a negligible effect on the motion. In the initial state, the skier has no kinetic energy. There is no elastic potential energy in both the initial and the final states. The skier has gravitational potential energy in both the initial and the final states. Finally, work is being done by external forces since the skier is said to be using his poles to propel himself across the snow. This work is positive work since the force of the snow on his poles is in the same direction as his displacement. Observe that the bar for work is an upward bar. This is consistent with the fact that the work done by the poles is positive work. Whenever positive work is done by external forces, the W external bar will be an upward bar. Note also that the sum of the bar height on the left side, +5 plus +2, is the same as the sum of the bar heights on the right side, +4 plus +3 of the chart. As mentioned earlier, the exact heights of the individual bars are not important. It is only important that the bars exist, that they are in the correct direction, upward, and that their sum on the left is the same as the sum on the right. Let's review some examples over the next few pages. A ball is dropped from rest from a tall bridge. As the ball falls through the air, it encounters a small amount of air resistance. The final state of the ball is the instant before it strikes the water. A volleyball player strikes the ball at just above net level and drives it over the net. The initial state is the ball just prior to the spike. The final state of the ball is the instant before it strikes the ground. A spring-loaded projectile shooter is on a hill. The shooter is aiming across the valley at a tree house that is much higher than the hill. What would the energy bar chart application look like if you were to shoot the projectile into the tree house? In a physics lab, a Hot Wheels car starts at an elevated position, moves down an incline to the level ground, strikes a box, and skids to a stop. Consider three states for the car. State A is the top of the incline. State B is the bottom of the incline before striking the box. State C is after the car has been brought to a stop. On your own, use the diagram and your understanding of the work-energy theorem to construct bar charts for the motion from A to B and from B to C. Here's a quick review. Work, energy, and power are highly interrelated concepts that come up regularly in everyday life. You do work on an object when you move it. The rate at which you do the work is your power output. When you do work on an object, you transfer energy from one object to another. In this lesson, you explore how energy is transferred and transformed, how doing work on the object changes its energy, and how quickly work can be done. We've just reviewed what we have learned so far, and now we're going to add some additional facts about work and energy. We have discussed that terms have specific meanings when they are used in science and engineering, and that these meanings can be quite different than the everyday connotation we associate with them. This is especially true of the term work. In science and engineering, work is defined to be the application of a force through a distance. This definition of work has several subtleties. First, if a force is exerted on an object, but that object does not have a component of displacement along the direction of that force, there is no work done on that object. Moreover, if a component of force is in the same direction as the displacement of the object, that component of force does positive work on the object. If a component of force is in the opposite direction as the displacement of the object, that component of force does negative work on the object. A joule is the unit of work. 1 joule of work is performed when 1 Newton of force is applied through 1 meter. A more conventional unit of work, commonly used from a nutritional point of view, is a calorie. 1 calorie equals 4.18 joules. This, however, should not be confused with the calories indicated in nutritional labels. There, 1 nutritional calorie equals 1 kilocalorie equals 4,180 joules. Work is a scalar quantity. Like the distance shown in the figure and the speed shown in the other graphic, these values only have a magnitude associated with them. No direction is required. So, what does positive and negative work mean? If a force pushes in the same direction as an object is moving, that object will speed up. If a force pushes in the opposite direction as an object is moving, that object will slow down. Thus, when positive work is done on an object, it speeds up, and when negative work is done on an object, it slows down. Take a minute to work this problem on your own. Also on your own, draw the free body diagram. Then click for the answer. Take a minute and work this problem on your own. We can find the net amount of work that is done on an object by a group of forces, but what does this value tell us? Recall that force times the distance, where force and distance are parallel to each other, gives the amount of work done by an individual force. Since we want to determine the net work done on the object, perhaps we should calculate that work using the net force acting on the object. So what is the net force on this object? It is the vector sum of the three forces. Note, F1 shows 1 in the x direction and 5 in the y. F2 shows -3 in the x direction and -2 in the y. F3 shows 4 in the x direction and 0 in the y. If we add these together, we find the net force. The net force is 2 in the x direction and 3 in the y direction. If you move the object 5 meters to the right along the path of the arrow, you would need to multiply the 5 meters times the total length of the force vector to get the work done by the net force. The vector's length is actually the square root of 13 because of the Pythagorean theorem. Work is defined by the application of a force through a distance. Energy is defined to be the ability to perform work. There are a few types of energy that we will focus on initially: kinetic energy, energy of motion, and potential energy, and energy of position. That is, by putting an object in motion, like a heavy truck, you give it the ability to apply a force through a distance. Likewise, if you were to pick that heavy truck straight up, you could give it the ability to apply a force through a distance by simply changing its location. We will discuss potential energy in greater detail in the next lesson. Returning to our previous result, we see that a net amount of work done on an object results in a change in the speed of that object. Also, if we define the quantity as the kinetic energy of the object. Potential energy is mechanical energy that is stored in the object. It primarily is encountered in two forms. The first form is energy relative to a position in a gravitational field. Lift a ball to a certain height above the ground and it has gravitational potential energy. The second form is energy that results from stretching or compressing. When compressed or stretched, a spring gains potential energy. During each month, you use energy to cook and light the place where you live. At the end of the month, you get a power bill. So it should not be surprising that energy and power are related. Your text defines power as the rate at which work is done. This is a good definition for our needs now, but perhaps a better definition for power would be the rate at which energy is transferred from one system to another. The horsepower unit was historically derived from the amount of work that an average draft horse could do in a single day. Let's look at an example problem. A 1,000 kilogram car accelerates from 10 meters per second to 20 meters per second over a distance of 85 meters. What is the minimum average power supplied by the engine that would accomplish this? Take a few minutes and work this problem on your own. Read the information and make the calculation. Take a minute to review the work-energy theorem. Note that capital W is work done by a non-conservative force that equals energy minus energy initial. Capital U is potential energy and lowercase g is gravity, while SP is spring-based.